It's good to be here. It's good to see all the students out there as well. And looking at some of the student posters is going to be exciting. So I've worked on quite a few radar programs at Sandia over the years, probably 20 plus years working on radar programs. So I'm going to kind of go over some of the developments we've had with that and talk about Pathfinder, GEOINT, and ISR development at Sandia Labs. One of the things I'd like to point out on this intro slide is our website at the bottom down there, just sandia.gov/radar. That site actually has a lot more information on radar background, how these radars work, than what I'm going to give here today. So if you're interested, feel free to go to that website. And I'll repeat that again at the end of the talk. I've got that website again, but I know the end of the talk is dangerously close to lunchtime, so you might be heading for the chow line by then. So here's the overview for the talk, and it kind of breaks down into giving a little bit of background and history, how we got where we are today. We're going to talk about some of our current capabilities, the focus areas that we're currently looking at in the radar area. Then I'm going to finish up with a look at what's coming down the road, kind of looking further out, seeing what we see on the horizon in the realm of radar technology. So with that, let's take a quick look at how Sandia operates. So Sandia was started in 1949, just a few years after our friends at Los Alamos up on the hill there. We're also a Department of Energy laboratory. We've been managed by a few different industrial entities over the years. We started out with AT&T back in the 40s. They managed us very well for a lot of years, up until '93, and now we're currently managed by Lockheed Martin. We are a government-owned contractor-operated facility, so a GOCO, and we're also a federally funded research and development center. And basically what the FFRDC means is that we have quite a bit of latitude in forming partnerships with academia, with government, with industry, and we can act in a number of different roles as well. We can be developers, we can be reviewers, we can be a tech partner with the various people that we partner with. We do a lot of CRADAs and have quite a few different partnerships with people all across the country. So of course, Sandia is fairly well known for its nuclear weapons competency. And back in the 40s, that's actually how we became involved in the radar business. We designed the fusing systems for some of the original weapon systems. Then, starting with that tech base, we transferred that over into airborne radar, synthetic aperture radar to be specific, and taking what were basically radar altimeters, expanding that technology all the way up to these very sophisticated imaging radars. And then to complete that circle, we try to take that technology that we develop in the airborne world, in the airborne radar world, feed that back into these NW systems so that they take advantage of the latest technology that we've developed on the airborne side. So once we got going on developing synthetic aperture radar, you can see there's been a continual evolution in terms of what capabilities these radars provide and in the size and weight of the systems as well. It's like everything else, we can do a whole lot more now with these very small systems, these very small chassis, than we could do back in the 80s, when they were these big giant boxes. So essentially we've been working on improving radar performance and reducing the swap of these systems for about 3 decades now. So that kind of gets us back into where we are today. On airborne ISR at Sandia, and this is one of my favorite slides here because it gets kind of to the heart of what our airborne program is about. We've got at the bottom there of this pyramid, you've got the collected physics. and that's understanding how radar scattering works, how the different bands, X band, KU band, KA band, how that works with the environment, all the way up to the decision maker at the top of this pyramid, who's really looking for intelligence and information. So there's a lot of technical challenges for airborne intelligence, surveillance, and reconnaissance all the way up this pyramid. I mean, at every level of this, there's a lot of technology that goes into advancing the state of the art at each one of these levels. But ultimately, when it comes down to it, that decision maker at the top, he doesn't really care so much about the bottom there. What he wants is something that can deliver actionable intelligence to him. So we're trying not to just provide an appliance and say, here's your radar, go bolt this onto your aircraft. We're trying to deliver this entire system solution. So let me give you an example of a decision maker. We have a system that's operating in the Antarctic that the C-130 pilots that bring supplies down there, they have to come in and land on essentially a sheet of ice. And there was an issue there that certain times of the year there would be crevasses that would form in that ice, and these pilots would like to know that they're there before they come in and land. And it turns out that with blowing snow and all that, they get covered up optically, so you can't just look down there and see that they're there. So that's the kind of information that we're trying to move up this chain. That pilot, he doesn't want to know how X-band radar scatters off of ice. He wants to know, information that he can use that says, yes, there's a darn big crack in the ice there or not, so he can land this thing safely. So here's a couple of pictures that show some of what our focus areas are on. We primarily focus on high-resolution real-time SAR. So in the case of the Antarctic SAR, we need to form that image. We need to get all the information to that pilot right then, and make sure that he's got everything he needs to land that aircraft safely. So we focus on high-resolution real-time SAR and derived products like video SAR, which is just SAR in motion, and on coherent change detection. And that's what you see there in the bottom picture, where you can see accumulated change that happens over a period of time. So if you're not familiar with SAR in general, just as a sensing modality, it's really cool technology. I kind of place it somewhere on the cool tech scale, somewhere between kind of Siri and Google Now, maybe. It's really pretty cool. I've seen a lot of iPhones out here, so I might have that reversed. It might be between Google Now and Siri. I'm not sure. But anyway, since SAR is an active sensor, so we actually transmit a signal that bounces off the environment. It comes back. So since we have our own source of illumination, we can image day or night. We can image during a lot of different weather scenarios through clouds and smoke and dust and things like that you wouldn't normally be able to apply an optical sensor in. If you look at these images, take a look at the top one there. At these kind of resolutions, they're very optical-like. You look at that and you think, well, that almost looks like a photograph, a black and white photograph that somebody took. And that does make them easier for analysts to look at, to interpret, to find the information that they're looking for in that image. We're going to come back to that in a little bit about how they're optical-like, but not quite. They're pretty close. But that does get into some issues around training and other things. So there's good and bad that comes with that optical-like characterization of the data. So these are all examples of real-world applications that we've been engaged in since about 1997. You can see that we've been addressing critical problems pretty much all over the world, a lot of different geographical areas of the world. You notice kind of there in the middle, you see the round thing. It says Earth Sciences under it. That's actually a crater on the moon, so not exactly on the Earth. But that's from the Lunar Reconnaissance Orbiter that we had a part in. The guys from APL, from Johns Hopkins University, were the integrator for that, and we provided some key components. So I guess we do earth sciences and lunar science in a way. So the image in the upper right corner, the crevasse detection, that's a kind of a picture that shows you what the issue is there. The picture on the left kind of shows what it looks like from the air, just a blank sheet of white expanse. You can't really see the big crevasses in there, but when you light these things up with X-band radar, and they show up quite nicely, so you know if you're going to be able to land safely or not. So here we're showing that there are really multiple technical challenges for getting a SAR into any given mission space. We got to think about a lot of different things to make sure that we have mission success at the end of the day. So there's mission engineering. We're looking at TTPs and ConOps. There's real-time processing. We've got to get the system to produce these images in the time that we need them and be able to get them to analysts and the users of the data. Down toward the bottom, you see the analyst training. Analyst training is a big part of what we do, precisely because SAR is optical-like, but not exactly like an optical image that you would look at. So a lot of times the analyst will get these images and they'll look at it and go, oh yeah, I can see exactly what's going on here, I've got this. And we have to say, well, hold on, there's different phenomenology between what SAR does and what optical sensors do. And we have to go through and train them what to look for, train them how to analyze these synthetic aperture radar images. So all these things together, it makes getting SAR into the processing, exploitation, and dissemination cycle fairly difficult, just because of these challenges and things we have to overcome and people's perception of what SAR imagery is. So one of the things we found is that it's very critical, it's very key to understand the mission challenges up front. If we're going to ensure ultimate mission success, we really have to walk a mile in their shoes for understanding those mission challenges. Understand what they're up against, what they're looking for in the images, what their expected outcomes are. And there's quite a few other necessary components as well, the R&D part of it, system design, the mission engineering part, and training. And that all feeds into the ultimate mission operations. Of course, we never really get this right. We never get it, as perfect as we would like the first time. So we're always taking what we learn from the mission operations and feeding that back into this cycle to improve it for the next time. Of course, as soon as we get it where we want it, the mission challenges, they're always changing. They change out from under you, so you have to go back and re-engineer this whole cycle as the mission challenges are changing around you. And that's part of the challenge, and that's just part of the job. Okay, I'm going to switch a little bit and talk about some of our current radar capabilities. This list gives you an idea of some of the different modalities that we have, some of the image collection modes. And a lot of these work together. So for example, the arbitrary strip map and coherent change detection you can work those at the same time. So you can collect on a route. Say if you're trying to follow a road or some specified route, you can collect images along that route, which is a relatively fairly difficult thing for a SAR to do, actually. But we've got software in there that will actually track that road using some planning software. And then we can provide the coherent change detection, which is the white image kind of off to the left of the arbitrary strip map there. That shows accumulated change over some period of time. So as you make 2 passes past the area, on the second pass, you see everything that was changed from the first pass to that second pass. So in this case, you see somebody drove a vehicle in and turned around and then drove back out on the road. So one of the keys here is that as an FFRDC, we can often integrate all of these modes into all of our systems. We're not constrained to just build a system that's built to a specific spec, and we have to tighten that down and only have a few modes in it. We're always trying to add all of the modes that we develop into all of these the systems that we provide. And that's kind of what people are asking for, and that's the wave of the future, is that people want a wide breadth of missions from a single sensor. They don't want to have 5 things hanging off their aircraft. They want one box that does a lot, that does it very well. Okay? All right, here's an example of a video SAR. So again, video SAR is where we're taking an image, taking a SAR image, and we're flying around a circle or on a path, and we continue taking those images and then string all those together into a moving set of pictures. And we're actually doing this on our deployed systems in real time, so this is exactly what you would see if you're watching as an analyst. This is the gate into Kirtland Air Force Base. So you can see, in that shot right there, you can see the gates are open. You can see the reflection there as the cars are going through there. And you might notice some strangeness in those vehicles as they go in. A moving object in radar has a Doppler shift to it. And what that does is that places the return of the object outside of the image that you're looking at. So an object that's stationary, that return will collapse back onto that shadow area. A shadow area is just a lack of return. It's a lack of radar return, so it can't have a Doppler shift. It's always there, which is kind of a nice feature. So you can see the shadows as they go through the gate. Let's see. There's one spot here. Let me see if we can find it. When everybody's stopped at the stoplight, you can really see where all those returns snap back on. Okay, here we go, right about there. You see down at the left, the shadows, and then all the Doppler returns are snapping back on as they all stop at the red light. Okay. Anyway, they're supposed to be stopping there. They don't always stop. So here's another example of a video SAR. This is a concert venue just south of Albuquerque. It's kind of hard to tell from that optical photo on the left. But that kind of brownish area in the middle, that's actually a big grassy area, where you can get tickets and just go sit out there anywhere you want. And then the stage and the big vertical structure in the middle there is where the performers are at. So an interesting thing about this venue is anytime Albuquerque needs rain, I just go buy a ticket to this place and go sit in the grass. It's guaranteed to make it rain every time. But anyway, if you look at the SAR image on the right, it's kind of hard to tell where those vertical reflections are coming from, where the structures that you can see on the left side, where exactly they're placed in that image. But what I wanted to show you, and the reason I included this, if you put these things in motion, the brain really works well to kind of figure out that 3D placement of objects, tracking on the shadows and tracking on those reflections. So let's see if we can go ahead and get that video started. I think we just click on it. Let's see. Can we go back one? I think if we just click on the image on the right, it may go. On the right side. Right there, yeah. There it goes. Okay. So now you can see as we're flying around this thing, all those returns from the vertical surfaces, they start to make sense to your brain. You can start to see that there's actually something vertical there. You're starting to see the broadside reflections as you hit the chairs and the metal structures in that building. And you can see the shadows from light poles and things. Those things start to make sense to your brain as you watch these images rotating around. Okay. Right, there's a couple of advanced capabilities I wanted to talk about. And these can basically be summed up as saying we're adding more of what we already have in our single channel radars. So, if we add more channels to the radar, more collection channels, if we add more antenna phase centers, we can do things with that. If we add polarimetric orientations to collect full polarimetry, there are other things that we can do with that help us in detection and analytical value for that image. So this is similar to the way we started out with black and white TV back in the 50s, and then you went to color TV, right? So you added red, green, and blue channels. Then recently we go to high definition TV and 3D TV, and every time we add an additional degree of freedom to the system, we bring additional capability with that. It's the same thing with these radars. Adding multiple RF channels, adding multiple phase centers just allows us to pull more physics out of the scene and provide that as imagery and additional information to the people that need it. So we'll take a closer look at those two examples there on the bottom. The first one is this one, the high-resolution polarimetric SAR. And this is taking an idea from earth sciences where they use these polarimetric decomposition techniques. You've got the the 4 different polarization options there on the left. You've got the copole and the cross-pole images for horizontal and vertical orientations of the electromagnetic wave. Those by themselves aren't very interesting. You can see some differences in there. They look slightly different from each other. But the real value is when you start combining those things into these decompositions to create new information or to illustrate something about that scene that you're looking at. So for example, natural objects in these pictures tend to give you a lot of volumetric scattering. So think of that as going through trees and bushes. You're getting a lot of scattering off the leaves and branches and things. And that looks like a very specific decomposition with this method. Man-made objects, things like buildings and theaters, things like that, they tend to give you a lot of even bounce, so it's just going out, bouncing once, and then coming right back. You have flat surfaces and angles and things like that. They give you that, and they give you some helical scattering, so you tend to see those in these images as either yellow or kind of orangish and reddish returns from the image. So it almost looks like you're seeing grass and trees and things there. You're really not, but what you are seeing is how the scattering mechanisms were decomposed using this technique, and it actually looks pretty good. So Victor is another advanced mode, and basically this is combining a GMTI mode, so a ground moving target indicator mode, which uses these Doppler shifts that we saw before. And it also uses the ability to track the shadows of an object. So you saw the shadows going through the gate, the U-bank gate back there. We can actually track those shadows, kind of form a blob on that, and then track the centroid of that, and combine that with the GMTI return from this thing. And then combining that with the ability to continuously repoint the gimbal, which is sort of a new thing in SAR. Typically SAR, you point the gimbal at the scene center that you want to image, and you keep it there until you form that image. With this, we can point the gimbal, and then as we're tracking along with this shadow object, we can track the gimbal along with that object to track it through all the ranges of its motion. Let's see, I'm not sure if this one has a video or not. Let's see if we can click on that. Okay, there it goes. So. Anyway, the blue dots kind of showing these, the limits of the shadow centroids, and and as the object comes up and stops, and the GMTI return you see over on the right will snap back onto that shadow. Just lets us track an object through all of its range of motion. For example, if you're at an intersection, the car comes up, stops, and then turns off to the right. You could track it using this radar. It's a very difficult thing normally for a traditional SAR to do. Okay, I'm going to move on a little bit into our advanced radar test bed work that we do. This is our in-house facility for doing radar testing. FARAD stands for Facility for Advanced Radar Development. It's this cutting-edge radar SAR platform that's very reconfigurable, very flexible, that we fly on this Twin Otter aircraft. We fly that all around Albuquerque. We take it, places all over the United States to do data collects. We do work with both internal and external R&D efforts with this. One of the things that we use this for a lot is we'll have a customer who wants a data collection for a specific structure or a specific vehicle, and we take that and set up a series of test flights, collect a lot of data. Collecting data domes where you look at an object across all of its azimuth angles and all elevation angles, and then we can deliver that to that customer. Another thing that's come out of this FARAD is a lot of these polarimetric images that you see were done with this platform. And you can see since we have 3 different bands that we support with this, and these are interchangeable front ends that we can pull in and out. And you can see that a lot of these have multiple phase centers. The X band is fully polarimetric, so that's what we do a lot of those data collects with. But since this system is available for external use, if you have a need that you think might be able to use that capability, just let us know, and we'll see if we can set it up. Okay. So the next thing we're going to get into is advanced exploitation and automation. This is, again, kind of hitting some of the same highlights we've seen from earlier today and from a lot of the other talks here, that we're essentially drowning in this data from these sensors. We've got systems out there, deployed systems that are producing tens of millions of images per year. So you get a data pile that size. What do you do to look at it? What kind of questions do analysts want to answer with that? And they typically want to know, what happened, where did something happen, when did something happen, what are the relationships between objects in the images? Is there anything in the image that's changed? So our data analytics approach here is trying to help analysts make sense of all these millions and millions of pixels that we're producing. These images are generally quite large, up to 8,000 by 8,000 pixels, and it becomes very difficult to try and do a search on these things after the fact when you've got terabytes of data sitting there on the disk. So what we try to do with this is take these individual pixels, right? You got a lot of pixels there. Those form themselves into structures, vehicles, roads, whatever. We're trying to elevate those things, trying to elevate the abstraction of those dots on a map to something that's searchable, something that's node-based, a semantic graph that then an analyst can go in there and ask the questions that they really want to ask about. And these graphs represent the spatial and temporal relationships between the features that are on that map. So the airline flight map that you see up there, that was from a single day, and I think it was 2014. They gathered all of the flight information data that the FAA had, and they started using these techniques on that database as an example of how you can rethink the way you do search if you encode this data as mathematical trajectories rather than just dots on a map. So I'll talk a little bit more about that in a minute. But how does SAR fit into this? Well, SAR is great at determining patterns of life. You see there we got the SAR image with a stack of images below that. So we can use things like the coherent change detection to look at changes that have occurred over a fairly long period of time and start building up patterns of life. Combine that with EO and LiDAR, other data sets. It might be geographical location or something else. We combine those into these very complex semantic graphs. Yeah, and these, you see all the dots over there, there's a lot of relationships being represented there. But what it allows an analyst to do is come in and ask a question at a higher level of abstraction. And then the semantic graph can then say, well, based on what you're asking me to look for, I'm suggesting you look here, 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 and here. Rather than looking at the 10 million images you have out there, I'm going to give you some suggestions on how to focus your search. So it sort of helps with the needle in a haystack problem that you have amidst all these oceans of data. So going back to that FAA flight map for a moment, here's an example of this algorithm in work. So this was a clustering algorithm based on geometric features in all that flight data that you saw on the first page. And what this allows an analyst to do is he can go in there and say, well, I know there's a lot of data out there. Everybody's flying all over the country. But what I'm interested in are odd flights, things that don't match the normal template for a flight. So those might be mapping flights. They might be avoidance or holding patterns. But with this system, we were able to go in there and show that amidst all that data, we could narrow down based on their definition of odd flights. We could narrow that down to about 700 out of the total 50,000 flights across the US. So it lets an analyst get in there, ask very nuanced questions, and quickly spot things that don't belong. So now we're going to get a little bit into how human factors affect ISR performance. This is a huge factor in these operational ISR systems. Understanding the human to sensor interface, and it kind of gets back to the earlier talk about empathy, right? If you look at that, the binocular scanner up on the top, imagine telling somebody, put your face to this for 6 hours a day, and look at imagery. They're not going to be real happy with it, and a lot of times those factors aren't even really included in the acquisitions process. So somebody will say, hey, I want this thing that views images. It needs to view these things in 3D, and that's as far as it goes. They're given an appliance, they're given an instrument, without really thinking about what the human factors impacts are to that. So that's one of the things we've been trying to address in our PED cycle for SAR and ISR. It helps to optimize the workflows and the analysis of the data. So, for example, we use things like eye trackers. So we can watch these expert analysts and see where they're actually looking on the screen and where they're clicking. They'll click on their mouse and they'll take some action based on that. File this away or mark it or something. We can record that whole process and then learn from what the best of those guys do, and then train everybody else to sort of mimic the experts in that. So we do have quite a bit of breadth of expertise on staff. For example, we have an anthropologist that will sit people down and says, tell me how you use this piece of equipment or this piece of software, and she's very good. She thinks of things that the engineers don't typically think of, right? Because we're kind of geeky and nerdy, and we think anybody could do this. But she'll look at it and say, no, you can't have someone look at these images for 6 hours straight, or she'll look at how they're operating and then make suggestions based on what she sees and feeds that back into the whole PED process. So here's an example of one of our deployed systems where we applied these processes. We looked at crew selection, how they were being trained, how these teams work together when they were put into these small PED cells. And we did this as part of the analysis of the overall mission effectiveness. We knew what rate our radars could produce images at, and we knew how big the images were and all those things. But there's more to it than that. You have to put these guys in the cell. We know what they're looking at on their screens. We know how fast they're coming. So we have to really optimize that environment as well, and that's a critical piece of the mission effectiveness. In a lot of cases, these guys may be looking at a new image, every few seconds or so. So how long does it take them to start fatiguing? The human's eye is going to fatigue after a while looking at the same thing. So in this case, we, after studying these guys, seeing how they work, one of the results that came out of this is, well, we really can't have them there more than a couple of hours, or we're gonna start losing effectiveness in the mission. And that's that gets to be very important when these guys are looking at thousands and thousands of images per day. Right, I'm going to now shift over to kind of looking down the road a little bit, looking at what some of our future radar directions are. And see, the first thing up is just sort of a radar modernization effort. We've had some systems out in the field for quite a while. We're always updating those systems, using the latest and greatest technology. So this is our latest modernization effort, going to VPX multi-channel radar chassis, trying to get that in place for all of our systems, so that we can have a common system across all of these systems, the large systems, small systems, basically everything that we have out there. Trying to use as much COTS hardware, COTS components as we can, keep the cost in line, and do more in that smaller chassis as well. We think this will enable a lot of new capabilities as well. Just having the common set of hardware and software, and having very capable hardware. So the multi-channel concepts, tracking capabilities, mover detection, things like that are difficult to do now, we'll be able to get into this more modern chassis. So this is well underway. We've been testing quite a bit of this already, and we're looking forward to getting that out in the field as well. So then looking just a little bit even further down the road, we're looking at next generation systems. We call this next generation +1. And as these systems continue, they're going to continue to evolve to a generic hardware platform with multifunction capabilities. And they're going to have more of the things we've mentioned before. More multi-channel, doing more digitally, and making these systems more adaptable. That's going to be a requirement for the future. They have to adapt to changes in the environment, changes to the way they're being operated and the environment that they're operated in. We're also looking at incorporating a lot of the emerging high-speed hardware. There's high-speed DACs and ADCs and FPGAs and GPUs, all the cool tech gadgets that are always coming out. Always looking at incorporating those, getting those in for improving our processing capabilities as well. One of the things that's clear is that for the future, we're going to need high performance, real-time computing, and systems that can support multiple missions at the same time. Nobody ever comes to us and says, you know what, guys, you're doing too much here. Let's scale all this back, right? They always want more. They always want more images. They always want more capabilities. So, I'm sure you guys hear the same thing, but everybody wants to do more, smaller package, smaller systems, and that's what we're trying to oblige here. So this kind of gets us to our ultimate goal. This is looking even further down the road. This is kind of where we want to be, several years from now. Ultimately, what you really want is you want a multi-mission radar. You want a broadband digital radar that can do a lot of different things, a lot of different functions. You want it to have all these bells and whistles of waveform agility, channel agility, beam agility, and then even more of these multis that we've been talking about, multi-phase center. Multi-channel transmit receive modules. We've been working on those recently. Having multiple channels of this high-speed ADC and DAC, so that we can bring in entire RF bandwidths of the radar into the system and have more flexibility in how we process that. Again, adding the adaptive processing to it and having these data analytics piece that we've talked about, pushing more and more of that into the system as well. So there's lots of challenges here. There's lots of data being shipped around in the system. A lot of data processing that has to go on to process that data. But that's the kind of thing we like to do, and that's what we love to do, and it's where we're heading in the future. So I think that's all I've got. Any questions or anything else? I'd be happy to answer.
We do have a few. Thanks, Bert. We actually have a few from the audience here.
Okay.
And they're kind of, well, the whole presentation was kind of technical, so let's go through them. I like this one, right? So what's the state of the art in foliage penetration? Are we getting better? And how close are we to the ultimate end state, which would be complete visualization through canopy? I think we've spent the past 15 years fighting in deserts.
Right.
And we've had a lot of advances in LiDAR.
Right. Yep.
And Southcom isn't so happy with that, right?
Ah,
when they're dealing with canopy, and I'm sure Paycom also.
Right.
Can you talk a bit about that?
Yeah, a little bit. So canopy penetration is primarily a function of the band of the radar that you're operating. So that foliage penetration typically drives you to lower and lower frequencies, and that gets into the multi-frequency, multi-band radars that we'd like to have in the future. So instead of operating at KU and KA band, where you get very little foliage penetration, you need to push those bands down. Push the radar band down to really be able to look through penetrate through the foliage. There's also some other techniques that we've been looking at using these polarimetric decompositions that lets you see things along a tree line, at least. So, I mean, it's not looking into the trees, but it helps you with activities in other places as well.
Great. Second question, what level of compute is required to create those nifty real-time video SAR streams that you had, and what form factors are they coming in?
It turns out that modern GPUs, they can handle the load that we're doing, the rates that we're doing for these video SAR right now. So with, think of what your son probably has in his gaming computer, right? A nice NVIDIA graphics processor. Right. That's really sufficient to do the kinds of rates that we're talking about here for at least basic video SAR. As we start making the videos bigger and bigger, then you need more and more compute processor. But the nice thing is those GPUs and processing hardware seems to keep up pretty well.
Great. And then with all the open source data analytics, you showed kind of substantial software investment in what you were talking about. Right. Is any of that in the open source? Is there open source data analytics or kind of research harnesses that people can take advantage of from what you're doing?
I think a lot of it was developed in-house. So from that standpoint, since we're an FFRDC, we're always open to partnerships, creatives, tech transfers, all of that. I'll be honest, I don't know exactly how much of what the data analytics piece is using is based on open source and how much is developed internally. But we tend to kind of add the magic sauce to the open source things, and then that's the piece that we kind of hold a little bit closer. But yeah, I think we're always open to sharing whatever we've got.
Great.